So one of my personal favorite classification techniques is called logistic regression. Even though the name has regression in it, it's actually a classification technique. Don't be carried away by this term regression. It's actually a classification technique, not a regression technique per se. But of course, you can always modify some classification techniques to regression techniques. But logistic regression is a classification technique. It's one of my personal favorites. Now we'll understand the geometric intuition behind it. It's a very, very simple algorithm. It's a very, very simple, geometrically very elegant algorithm. By the way, I personally prefer understanding things using geometry. For example, if you remember, we learned naive Bayes, right? For naive Bayes, we didn't see a lot of geometry. We learned it through probability because it is a probabilistic technique. Techniques from now on, most of them will be very geometry oriented or logic oriented. Like I'll write LR for logistic regression. This is super geometry. There is a very, very beautiful geometric intuition to this. And by the way, if you take logistic regression itself, logistic regression can be understood from multiple perspectives. Remember, whole of machine learning has been understood by people from different areas of mathematics and sciences. Logistic regression, we can understand it using geometry. We can derive the whole logistic regression formulation using geometry. We can also do it using probability from probability. We can also derive logistic regression using something called loss function or loss function based interpretation. There are multiple interpretations to this, by the way. And what we'll focus on, especially in this course, because geometry is much more visual, it's much more easy to understand using geometry. So we'll focus, especially in this course, we'll focus a lot on geometry. We'll touch upon the probabilistic interpretation, but not dive deep too much. Because the mathematics involved, the number of equations, the number of proofs is slightly dense in the probabilistic interpretation of logistic regression. But what I will do is I'll give you an introduction to the probabilistic interpretation of logistic regression. But I'll give you some reference material that you can read up if you're very comfortable with probability. We'll also go through the loss function interpretation in full detail. So using all three of them, you'll arrive at the same formulation. You'll arrive at the same solution for classification using logistic regression. But there are three ways to interpret it, right? So different professors, different faculty, different textbooks could take different approaches to it, right? I've seen some books which take a probabilistic approach to deriving logistic regression. They basically go from naive Bayes and extend it slightly to reach logistic regression. The geometry is what I personally prefer because it's much more intuitive, because diagrams help us understand what's exactly happening. So I'll start with geometric intuition. I'll also give you some probabilistic interpretation with some reference material. I'll also dive into the loss function interpretation of logistic regression. By the way, many techniques have multiple interpretations. So we'll focus on geometries to start with. So we'll start with the geometric intuition of what logistic regression is. And let's see what it is. It's very, very elegant. Imagine if you have two classes of points, right? Imagine if you have two classes of points. Let's assume these are all your negative points, right? Negative class points, right? So this is your negative class point. This is your negative labeled class point. And the orange cross. And let's assume I have a blue cross here, right? Let's assume I have a blue cross here, which is all the positive points. Okay, my blue cross here is a positive class point, is a positive labeled data point, right? Now, to separate both of them, the first thing you'll notice quickly is I can draw a hyperplane. I can draw a line. This is 2D, right? In 2D, I can draw a line. In 2D, I can draw a line. And in n-dimensional plane, a line simply becomes a hyperplane. A line simply becomes a hyperplane, right? So if I can somehow separate my positive points from my negative points using a plane. Planes are typically represented with a pi, right? This is the plane that I want to find out, right? So if my data is linearly separable, this word is very important, is linearly separable. And what does linearly separable mean? Linearly separable basically means that there is a line or a plane that can separate my positive class from my negative class. That's what it means to be linearly separable, right? And there is also a term called almost linearly separable. Almost linearly separable. What it means is most of your data is almost linearly separable. There might be some errors. For example, you might have a positive point here. So you might have a negative point here, or you might have a positive point here. Now this data is almost linearly separable because most of your points, except these 2 points, all of your points are being perfectly separated using a linear surface. So planes and lines are called linear surfaces. They are called linear surfaces because we'll see why it's called linear surfaces. Just to give you some context here, what is the equation of a plane? So lines and hyperplanes are considered to be linear surfaces. Your quadratic surfaces, there is also something called as quadratic surfaces. Your quadratic surfaces are stuff like circles, your parabolas, right? Ellipses, they're all called quadratic surfaces, right? We'll see why they are called so when we look at the mathematics behind it, right? So for a given plane, remember, for a given plane, there is always a normal W, which is perpendicular to the plane. How do you represent a plane? How do you represent a plane? A plane can be represented with two parts, W and B, where W is the normal to the plane, where W is the normal to plane, right? Pi is the intercept term. Pi is the intercept term. Just to quickly recap your mind, what is your line in 2D? It's basically y equals to mx plus c, right? So this is the equation of your plane in line in 2D. Similarly, an equation of a line or a plane in high dimensional space would be w transpose x plus b equals to 0, right? This is the equation of a plane. Any plane pi can be represented with both w and b. B is called the intercept term and w is called the normal to the plane, right? Very, very simple idea. Nothing very fancy here. We discussed about the equation of a plane, etc. And we also said that if the equation passes through origin, if the plane pi passes through origin, if it passes through origin, we said b equals to 0, which means my equation of the plane becomes w transpose x equals to 0, right? Remember, in my general equation of a plane, what is my plane represented as? W transpose x plus b equals to 0, where x is a data point which belongs to a d-dimensional space, right? A w is also a vector in d-dimensional space. If w is not a vector, I can't do w transpose x, right? And b is a scalar belonging to one-dimensional. So b is a scalar, x is a vector, a d-dimensional vector, and w is also a vector in d dimensions, right? So this is a quick recap of what the plane equation is. Now imagine if my data is linearly separable or almost linearly separable. That's the assumption that logistic regression makes, right? So the big assumption that logistic regression makes, so the big assumption of logistic regression is that my classes are almost linearly separable or perfectly linearly separable. They're either almost linearly separable or perfectly linearly separable. That's the assumption that my logistic regression is making, right? And now if I have a bunch of negative points here, now imagine if I have a bunch of negative points here, and if I have a bunch of positive points here, right? If I have a bunch of positive points here, right? Now my plane will look like this, right? My plane will look like this because it's separating both these points. Let's assume there are also some errors, right? Imagine if I have a negative point there, and imagine if I have a positive point here. So this is almost linearly separable, right? Except for these two crazy points, which are not perfect, but that's okay. Except those 2 points, all the points can be linearly separated. And what is the equation of my plane right now? My plane has a normal of w, and my plane can be represented as w transpose x plus b. Now, when my plane is represented as w transpose b, so what is given to us? You are given both the positive data points and the negative data points, which means you're given all of these points, all of the blue points and all of the orange points, right? This is already given to you. What do you have to find out? You have to find w and b, because if you find w and b, you have discovered the plane, right? That's a task here. The task in logistic regression is to find w and b, which corresponds to the plane, such that this plane separates your negative points from your positive points from your negative points. Right? That's a task. The task is very, very clearly, it needs to be understood. Task is find a plane pi that separates, that best separates, I should say. Because sometimes it may not be perfect, right? Because you have these two errors here or two outliers. That best separates your positive points from negative points. Your positive points from your negative points. That is the task of logistic regression, right? And this is the assumption that logistic regression is making, that your data is almost or perfectly linearly separable. If it is not, logistic regression cannot be applied. Okay, this is the fundamental assumption. Remember, what was the assumption in your naive Bayes? Your assumption in naive Bayes was conditional independence of features, right? So every model makes some assumptions. K nearest neighbor. What is the assumption? That the neighborhood of a point is same as the point. Okay, so every model makes some assumptions. Logistic regression makes an assumption that your data is almost linearly separable. Now our task, let's go back to our task. Our task is now to find a plane that separates your positive points from negative points. Let's go into the mathematical pieces of it, right? So let me just draw all my negative points first. Okay, let me just draw all my negative points and all of my positive points are here. The mathematics is very, very beautiful. The mathematics of logistic regression is something that I've enjoyed studying. And let's assume I have a positive point here and I have a negative point here. And let's assume this is the plane that I want to find. This is the plane pi that I want to find, and this is the normal to the plane, right? Then let's look at it. Let's try to pose this as a problem. Let's go step by step. Now, given any point xi, so let's assume this is a point xi. Let's assume this is a point xi. What is the distance of this point from my plane? Let me call this distance as di, right? So given any point, either the positive point or the negative point, let's start with this. Let's assume all my positive points, I will write yi equals to +1 for positive points, right? For negative points, I will write it as -1 instead of 0. Remember, this is a very important distinction. Sorry, I wrote +1 here. I should write it as -1, right? I will write it as -1 for negative points. This is important. Till now, what have we been saying? We have been saying 1 is plus positive points and 0 is negative points. This is what we have been saying till now. Now we'll change it slightly. That +1 represents positive points, -1 represents negative points. You'll see why I'm using +1, -1 and not 1 and 0. We'll see that in a while, right? So please bear with me. We are saying that +1 means positive points. These are the class labels. Your yi now belongs to -1 comma +1, -1 comma +1, right? This is what I'm assuming. Of course, the binary, right? At the end of the day, it's all binary. I can choose 1 or 0 or -1 or +1. Now let's go to the mathematical parts. So imagine, so for all these points, for all positive points, it will be +1. For all negative points, it's -1. Now let's compute the distance of a point from the plane, right? Any point. There could be this point or this point. Let's take this xi now. What is di? Di is the distance of this point from the plane. And I can write di as w transpose xi by length of w. We saw this, we derived this in the basics of linear algebra, right? Now, we are assuming that w is the normal to the plane. W is the normal to the plane. We are assuming that w is the normal to the plane. That's what we started off with, right? So now let's assume w is a unit vector. Let's assume w equals to 1. What does this mean? It means it's a unit vector. If w is a unit vector, I don't have to worry about norm of w, right? If w is a unit vector, then my distance di is nothing but w transpose xi, because the denominator has become 1, right? So I can just discard this denominator now. So my distance to a point is w transpose xi. Now let's look at a positive point or point which is in this side. Now if you take any of these points, since they are in the same direction as w, right, for this di. So let me take two examples, okay? Let's assume this is di. Let's assume this point is xj, right? And this is dj, okay? So when you compute, right? So di is W transpose Xi, and Dj is also W transpose Xj. Now look at what happens, right? So your Dj, when I compute Di, which is equal to W transpose Xi, since W and Xi are on the same side of the plane, see W is pointing in this side, right? W is pointing in this side. Since W and X are on the same side of the plane, you will get this value to be greater than 0. Now take Dj. Dj is W transpose Xj. Now look at it. Dj, because Xj is on the opposite side of your W, right? This value will be less than 0. So what happens is, so for all positive points, so if I say, finally, let's assume I found a plane. If I say that every point that is on the same direction, as my W are all positive points, all the points which are on this side are negative points, right? So let's assume that is the final classifier that I built. So how does my classifier look? My classifier will look like this. My classifier says, if W transpose Xi is greater than 0, then Yi equals to plus 1. If W transpose Xi is less than 0, then Yi equals to minus 1. This is what my classifier will look like. Because once I discover a plane, I'll say everything on this side of the plane, everything on this side of the plane are all positive points. Everything on this side of the plane are negative points. Of course, I'll make mistakes because this point is actually negative, but I'm classifying it as positive. And this point is actually positive, but I'm classifying it as negative. I'll make these mistakes. But my decision surface, remember, my decision surface in logistic regression is a plane, right? Is a line or a plane, right? It's a linear surface. Because one side of it, I'm calling it as positive points. The other side of it, I'm calling it as negative points. Now comes the fun part, right? So if this is what I'm saying, now comes the fun part. Now we said for all positive points, your Yi equals to plus 1. For all negative points, it is minus 1. So now let's look at a term. The term is this. If I have a term W transpose X. Now here, remember, I could also say plus B. Remember, I'm just saying that my plane is W transpose X. Some people may say, no, it's actually W transpose X plus B. Let's make some simplifying assumptions. Let's assume this plane passes through origin. Just for simplicity. Passes through origin. Let's assume. Of course, you can always change it slightly to add plus B here. Nothing is going to collapse, frankly speaking. Okay. So I'm just making some simplifying assumption. I don't want the plus B dangling here, which I need to handle later. I'm just simplifying it for myself. So if YAW transpose Xi, okay, let's see what happens to this. If Yi is positive, if Yi is plus 1, which means it's a positive labeled data point. And if W transpose Xi is also greater than 0, okay, what does it mean? My classifier is saying if W transpose Xi is equal to 0, my classifier is saying it's a positive point, right? So if the actual class label is positive, this implies my classifier is saying that it's a positive point. It's a positive point, right? So what happens to Yi multiplied by W transpose Xi? If this is greater than 0, right? What happens if this is greater than 0 for positive class, right? Then what does this imply? If this is greater than 0 and if Yi equals to plus 1, then my plane represented by W, my plane, right? My plane is correctly classifying the point. Because my plane now, because W transpose Xi is also greater than 0, my plane is saying that Xi is a positive data point. And the actual true label of it is also positive, right? This is case 1. Let's look at case 2, right? Let's look at case 2. Case 2 is, let's assume Yi equals to minus 1, which means it's a negative point. And let's assume W transpose Xi is less than 0. When W transpose Xi becomes less than 0, then your logistic regression is concluding that your xi is a negative point, Now what happens to it? Now if I take yi, w transpose xi, since this is negative and this is also negative, multiplying two negative numbers will become greater than 0. Right? So when I do, so this is for positive points, and this is for negative points. Right? So whether it's a positive point or a negative point, if yi w transpose xi is greater than 0, this is important. For both positive and negative points, if you take yi w transpose xi, and if it is greater than 0, what does this imply? This implies that the model, the logistic regression model is correctly classifying the point. Is correctly classifying the point xi. Right? That's what it means. And this is what we want. We want to find a w which does this. Now let's take the other case. Let's take case 3 now. Case 3 is this. Case 3 is that yi is a positive data point. And let's assume w transpose xi, we get it as less than 0. When does that happen? Let's look at this. So yi is a positive point, but w transpose xi, let's assume this is my xi. Since this is in the opposite direction of w, when I do w transpose xi, with this xi, I'll get a negative value. For this, right? Similarly, I'll get a negative value. Let's continue with the thought process. So if my point is positive, but if my plane, so what is this saying? This says my logistic regression is saying that my point xi is negative class. This is what it's saying, right? Then what happens? To yi w transpose xi? This will be less than 0 because this is a negative number and this is a positive number. When you multiply a positive number with a negative number, you get a negative number. So when this happens, what does this mean? When this happens, your true class label is +1, but your logistic regression is concluding it to be -1, which means this is a misclassified point. This is a misclassified point wherein the true class label is +1, but logistic regression is saying -1, which is exactly this point, right? Because its true label is blue, which means actually it is a positive point, but because it lies on this side of the hyperplane, my logistic regression, which is nothing but the hyperplane, is concluding that it's a negative point. Similarly, let's take case 4. The case 4 is, imagine if my yi is -1, which implies it's a negative class point. Now if w transpose xi is greater than 0, what does this mean? This means my logistic regression is saying that xi is a positive point, which means they both are disagreeing. What does this mean now? This means that this point is also misclassified. Right? And when this happens, what happens now? yi w transpose xi will be less than 0. Right? So when does that happen? Look at this point. Let's look at it geometrically. This point, my plane, my logistic regression, because it says all the points on this side of the plane, are all positive, but it's actually negative point, right? My yi is -1, but my plane or my logistic regression is saying that it's a positive point. In such a case, you also get misclassified points. So eventually, if you look at these 4 cases, what do you want? What do you eventually want? From case 1, you'll see that you want, see, at the end of the day, all of our classifiers, we want our classifier to be very good. What does very good basically mean? Minimum number of misclassifications, or you can call it as maximum number of correctly classified points. We want all of your points to be classified as correctly as possible. Now, what is it for all correctly classified points? If you look at case 1 and case 2, right? right? The summary of case 1 and case 2 is, if it's correctly classified, then yi w transpose xi is greater than 0. If it is incorrectly classified or misclassified, your yi w transpose xi is less than 0 in case 3. Also in case 4, it is less than 0. Right? So eventually, what do you want? You want to maximize correctly classified points, which means you want as many points. You want as many points as possible. You want as many points as possible to have yi w transpose xi to be greater than 0. You want this to be greater than 0, right? You don't want it to be less than 0. Right? That's your whole task. Your task is find a plane pi. And what is a plane pi? Nothing but w here. Find a plane pi or find w such that you have as many points correctly classified as possible. Right? So let's try to write it in a mathematical formulation. Okay. You want to maximize. Imagine I have n data points. Imagine I have n data points. What do we want to maximize? We want to maximize yi w transpose xi, where I goes from 1 to n. Right? I'm trying to write it as a mathematical equation. Okay. So what is it that I want to maximize? I want to maximize yi w transpose xi. Because if all these points are positive, imagine for every point, if this is positive, that's great. So I want to maximize this. Whenever you're trying to maximize, you want as many positive values as possible and as few negative values as possible, right? Right? That's simple. Now you're trying to maximize this term here. This is very important because you want these values to be as many values as possible to be greater than 0. So I'm summing them up, right? And now what is that I can change here? My xi comma yi pairs are fixed because they come from my data set dn. Given a data set dn, given a training data set, my yi and xi are fixed. What is the only thing that is a variable here? This is the only thing that can be varied or that can be changed, right? So we say, what is a task? Our task is to find the appropriate plane, right? So we will say that when you put w here in this max term, it means that this is a variable. Whatever you put here in optimization, again, we'll dive into optimization a little later. I'm giving you a very high level introduction. Whatever we've told in words here, I'm trying to write it as an equation, right? We want to maximize the sum of yi w transpose xi because whenever this is positive, we want for all points I this to be positive if possible. And as few points as possible, we want this to be negative. And we want to maximize this sum eventually. And what is the only variable I have? W. Which means, what does this mean? This means change w or vary w. Okay. And find, as you vary w, this sum will change. As you keep changing your plane, this sum will change, right? And I want to find a w that maximizes this. Right? There is also a slight different way of writing this, which is I want to find the best or the optimal w dash. Whenever you put a star in optimization, what it means is I want to find an optimal w or an optimal plane which maximizes. So you also use argmax. You remember we saw this in Python. We saw this function argmax in Python, but this is a mathematical optimization. We want the variable here. What does this mean? This means this is a variable that I can change. And what do I want to maximize? I want to maximize the sum of these terms. What does this mean? Now, this is very important. What this means is maximize this term of which these are constants because given a data set, they're fixed. My only variable is w, and whichever w maximizes this. Argmax basically means that. Argmax means whichever w maximizes this sum, call that variable as w star, right? So this is the optimization problem. This is the optimization or the mathematical optimization is a mathematical optimization problem that we want to solve. Because if I solve this problem, I'll find the optimal w star and that w will be my normal to the plane, right? But of course, we'll go and improvise this problem. Slowly, we'll improvise this problem. But this is the problem that I want to solve. in a nutshell. Of course, we'll improvise it and we'll take it into a form which is very nice and beautiful. But at the outset, from simple geometric intuition, this is what I want to maximize, right? Now, there are some problems with this that we'll solve step by step. But this is the whole core crux of the problem that I want to solve. Let me repeat it. Again, always read equations in sentences so that it will feel like poetry. It says that my optimal W, or the best W that I have, is that W which maximizes, argmax basically means that W that maximizes this value. And what is this value? This value is positive if you have correctly classified. If you have correctly classified, this point is positive. If you have incorrectly classified, if you have misclassified, this value is negative. And you're taking a sum of them, right? When you're taking a sum of them, you want as many positive values and as few negative values as possible. And this is a problem that we're trying to solve in logistic regression. Of course, there are some problems with it. We'll keep improvising this problem step by step.